Maybe I'll open on the blinds a little bit dark. Okay, that's good. That's okay, guys? Alright, so let's have a look here. Now, I typed the numbers into the spreadsheet here. So what was the first thing we had to do? We had to get the log. How many marks was that?
2 marks.
Do you know how to use your calculator? Then you should get 2 marks. So, log the activity. How many digits should I use? I think it's more than enough here to go for
2.
This is
It's 49. If you go with...
Yeah, if I go with 3 digits, 4 significant figures, I get this, right? If I go with 4 significant figures, the 9 here, I have to round up because of the 8. If the 9 goes up, the 9 goes up. If the 9 goes up, the 4 goes up. So the first one actually becomes 4.5. Okay, you should have something like this. Yeah? Right, what's next? Let's see. Show that. Okay, so that's a proof that we've done in class. It's only 2 marks and it's very short. You have A equals A0 E minus lambda T. Log A equals log A0 E minus lambda T, but the first rule of logs is plus, and then E and log cancel. So I get minus lambda T plus log A0. So that's that one for, what's it, 2 marks only? Yeah, okay. But the next one's 5 marks. So we want to plot this and this onto a chart. So obviously time goes on the X and log activity goes on the Y. Scatter plot, and this is log activity against time. The X is time in hours and the Y is log activity in mega equals, and you should have a chart like this, which I shall shrink a bit. So you should have something like this. I shall put in the line. So this is the graph you should have. Straight line going down. You got that? Very good. Use the graph to calculate the decay constant. So if you remember, the decay constant on the graph is equal to the minus of the slope. So you can work that out from the graph by drawing the triangle y over x. But the computer has done it for me already. So you should have 0.053 as the decay constant. So something like roughly 0.053. I'd say for the exam it probably has a plus or minus 0. I don't know how accurate they want this one.
0.052.
Yeah, it's fine. Yeah. Okay. And finally, what is the half-life? So the half-life is just log 2 over this number, which will be log 2 over 0.053 at 13.08 hours. And again, probably anywhere plus or minus 0.1 of an hour will be fine. You got 13.1?
Yeah, 18.
Yeah, okay. Not hard, right?
Oh, yeah, okay, so question. Remember the time when we had, okay, so it's 24 hours, I could say that's 12 hours half-life, right? Why can I say this time?
Where are you getting 24 from?
The final time?
Yeah. But if you look here, if you were to estimate it roughly from the graph, you start off with 90. So at what point does the activity become 45? That's the half-life.
Oh, yeah, okay.
Not quite 12, because at 12 hours it's still more than half, but not as much as 16, because 16 now is less than half. So if you were to estimate the middle of 12 and 16 as 14, so roughly from the graph at a glance, from the table, I would say any answer near 14 is bound to be right. So my answer of 13.1, you know, I can be confident in the exam I didn't do anything stupid. Yeah? You see why I think the atoms question is could be one of the best questions in the exam. We did the B part last time. I don't think, the only thing that was difficult in the B part was the use of English. Remember, with the toy ride? Yeah. Apart from that, all standard here. Okay, so we'll continue on the next lesson. It would have been better if you did that at home, but at least now I know that if you got a question like this in the exam, it should cause you no problems. In fact, you should be very happy if you got one like this in the exam. Okay. OMG. All you did for me is one graph question and now you want to take a 10-minute break. What's wrong with you? Seriously, that's the only thing you've done for me today, is do one graph question, an easy question. Why do you need a break?
We had 2 hours and 10 minutes before. No break before. Before
Yeah, but 2 of those hours is with me. So, you know, that's not as bad, right?
That's true, actually.
The next lesson is quite easy. And look, what did you have before the chemistry?
No.
Do you know your sister probably works like 24 hours, 30 hours in the hospital?
I think more.
Maybe more, 40 hours? Yes, exactly, yeah, 30 hours per day, yeah.
1 year.
And if she learned her little brother after 2 hours, oh, I need a break. I tell you what, Moucherie, stick with it for a few minutes, and if you feel like you're about to collapse and you need a break, just put your hand up and we'll have a break, okay? No, I don't want to hurt you. If you feel like you can't handle it, just let me know. Same goes for you guys, okay? Although I know Mir can handle it because he's been well rested. When's the last time you woke up before 9 o'clock now?
Many times.
Many times, really? Okay. Applications of radioactive isotopes, if you can write that down, please. The good thing, Moucherie, is this lesson is a picture lesson. Lots of pictures.
No, it's not good.
Ah, you're never happy. I don't know what I need to do to make you happy.
No.
Too many pictures, too many maths, too much English.
No, the picture in class is okay, but when you went home and you want to revise it, it will be harder.
Don't worry, I included words as well. Okay, can we start? So, radiation is not all bad. So far, all I've said about radiation is that it's very bad for your health. And of course, examples were alpha. I said alpha is very bad if you get it inside you. Beta is very bad if you get lots of it on you for a long time. And gamma is the most dangerous, but the good thing is alpha, you can stop it with your hand. Beta, you can kind of stop it with your claws. Gamma, you can't stop. But it's kind of the least dangerous insofar as gamma is not as common as alpha and beta. It's only in some situations where you get gamma, particularly in space. So on Earth, the radiation we deal with in a day-to-day life is alpha and beta. Alpha is easily stopped by your skin, so it's not that dangerous unless it gets into your food. Beta could even be stopped by your clothes. So, you know, it's not too bad, but not only is it not all bad, it actually has some applications, it has some uses. Now please note, the text in bold is extra important for the exam. Okay, so we're going to look at applications of radiation. So the first one, which is important for the exam, is something which you should all have in your home, called a smoke alarm. And there's one right there in the room. Now, I know you can't quite see the picture, but I can just kind of roughly draw it here. Yeah. Let me think, see if I remember this. So basically, smoke alarm is very, very simple. You've got a cell, of course. You've got some kind of alarm, so I don't know, well, I'll just write alarm here. And then here you have an electric field. I'll make it a bit bigger. So the current travels along here, and then you have an electric field. Like this. Yes. Now, and also let me just see. Yes. I believe this emits an alpha. Pretty sure it's an alpha. Yeah. I'll draw mine. I'll draw it here. No, I'll draw it here. Okay. So what happens here? You have your alpha particles come out, and because I believe it's alpha, because they're positive charge, they will want to move. Oops. Down here. So what will happen is you'll get a current here. Basically, this alarm is like a ammeter. So it's kind of like a milliammeter. It measures amps. Now, what happens is when you have smoke that enters it, because alpha is so easily blocked, when the smoke enters in the electric field, it blocks the alpha particles getting into the field and hitting the negative plate. Not only that, smoke, I believe, is usually negatively charged anyways. So it actually sticks to the positive plate. So this causes a notable change in the current. Previously, you had your current from, let's say this, I don't know, I'll just make up a number, it's like 9 volts. And let's replace this with a voltmeter. Because the positive gets added to this plate, it increases this, so maybe this gets boosted up to like 10 volts. But when the smoke comes along and blocks the alpha from hitting this plate, and the smoke is negative and hits the top plate, it reduces. So instead of being the battery increasing to 10, maybe it has the effect of decreasing it to 8. In other words, the alarm goes off if there's a change in the voltage in the other direction. You know, basically, the smoke alarm is just a simple circuit, and the smoke blocks the alpha radiation getting onto the plate and changing the current as the alarm expects it to change. So I don't think you need the diagram for the exam, although I do recommend the diagram for the exam. But technically the exam question is to describe. However, drawing a diagram can help focus your mind to describe it. But one type of use of radioactive material is to detect the presence of smoke or heat, but really it's smoke here. Oops. These ionization chambers, smoke detectors, are the most popular because they are inexpensive and are sensitive to a wide range of fire conditions. That should really say other fire conditions than the other type.
Wider range than the other.
I took this from a website where they were talking about different types of smoke alarms. There are other types of smoke alarms, ones that have some like glass inside of it, like a sprinkler, and if the room gets hot, or a piece of metal, and if the metal gets hot, what happens when it gets hot? Expands, so maybe it trips a circuit, you know. So there's many different types of smoke alarms. This one detects smoke, but there's ones that could detect heat. The ones in the accommodation, I believe, smoke and heat. No, I know from talking to them, it detects heat as well, yeah. So a couple of times when the room gets really hot, but there's no actual smoke, it just gets really hot because, I don't know, like, it was really sunny and the windows were hitting the room. The heat was coming in through the windows, and there was nobody coming in and out of the room, so no cold air was getting in, so the room just slowly warmed up. And then, you know, the alarm could go off just because it got too hot. So this particular type just works off of the smoke blocking the circuit. That's the key idea. The smoke blocks the circuit and sets the alarm off. Now, you can write it in your own words, you can draw a picture, but whatever, you could get a question in the exam that says, describe how a smoke alarm works. Probably the easiest thing is to describe it in words. But a diagram can help you if you want to draw a diagram. I don't know, what do people think? Words, diagram?
Words.
Okay. So, and also, the name of the radioactive material that's used to make the alpha in the smoke alarm is called americurium-241. You would want the name. It's a radioactive material like uranium. It's on your periodic table. Let me just change this a little bit for you so you can write this down. One type of radioactive material is to detect the presence of smoke or heat sources. These ionization chamber smoke detectors are the most popular because they're inexpensive and are sensitive to They contain some americurium. They work by detecting a break in the circuit. Okay, if you want, you can write this down. Does anybody know why I have the square brackets around some of my words? What I've done is I've taken a quote from this website. But whenever you alter someone's quote slightly to help it read better, or because you need it to fit, or just because the context here is different than on the web page, you put square brackets. So, for example, this probably started off with one type of the several we have looked at. So I just deleted that and changed to one type of use. You know, so you can slightly alter quotes. But you must indicate to the reader with square brackets where the alteration is. And the ... in a quote, what does that mean?
You were saying something more.
Yeah, and I deleted that again for reasons to make it fit into what I'm saying here. So, one type of use of radioactive material is to detect the presence of smoke or heat sources. But I think for us, we'll just go with smoke. These ionization chamber smoke detectors are the most popular because they are inexpensive and are sensitive. They contain americurium. They work by detecting a break in the circuit.
We don't have to write the word you get or something.
No reference required in the exam. I've changed the quote so much it would have been easier just for me to write my own one at this point now.
these ionization chamber smoke detectors are there. What these? Which one these?
These ionization chambers, as in these smoke alarms we're looking at, they're called ionization chamber smoke detectors. Because chamber, you know this word?
Chamber.
Like, well, chamber in a gun, that's true too, but chamber usually mean like a small volume. So the small volume here is this. If I just go back to the picture. This is called, see this part here? Is the ionization chamber, where the alpha particles hit the negative plate.
We have done it in
Huh?
we have done this in chemistry, ionization.
Have you? Ionization chamber you've done in chemistry?
Mass spectrometry.
Yes! Yes, like this. I don't quite have my picture right for how the smoke alarm works. It's not exactly like it is how I'm showing you. But the key concept is that it works by detecting a break in the circuit because the smoke blocks the ionization radiation coming into the chamber. Continue?
Yeah.
Yeah, Musharif? Mir?
Just give me one second.
Which word are you on?
Last one.
Okay.
The work by detecting the plate from the cycle.
Yep, okay. This is one of the applications you need for the exam, for sure. Okay. The next one, so another bit of information up here. Smoke alarms use americurium-241. The half-life of a of americurium-241 is 400 years, meaning that this will still be good for a couple of hundred years. Of course, the rest of the alarm won't be, because the circuit and the metal will corrode in the alarm before the americurium becomes less radioactive. But 400 years is pretty long. I don't know if americurium-241 occurs in nature or if it needs to be man-made in a lab. I'm not sure actually. Okay, the next one, fluorine-18. Half-life of only 2 hours. And you can kind of see the picture here, what's happening. So this person here knows there is a leak in the water supply, in the pipe. And you want to know where it is. Now the problem is, pipes are underground. So you can't see where the water is leaking out. Because you have this problem in most countries, like in Ireland too. A pipe will burst underground and the ground will fill up with water. And the only way you know that the pipe has burst is because here the pressure will be lower than what you were expecting than say what it was here. So if this is, a 10-kilometer pipe or even 1 kilometer pipe, you can't really dig up the whole ground for a kilometer to find where this hole is. So a very smart way to figure out where the leak is you put this fluorine-18 in the water. So what you would do is you'd cut the water off, maybe, so that people don't drink it, and put it into the water at the start here. The fluorine moves with the water, but then when the water leaks out here, it leaks out with the fluorine. You can use your Geiger counter that we saw last week to detect where there's radiation in the ground. His Geiger counter will tell him there's radiation here. That means there's the leak here. So a radioactive tracer, and this is called fluorine-18, or also called a radioactive label, is a chemical compound in which one or more atoms have been replaced by a radioisotope. So, by virtue of its radioactive decay, it can be used to explore the mechanism of chemical reaction or movement by tracing the path that the radioactive isotope follows from reactant to products or from source to sink. So one application here is to find where the leak is in the pipe. But another application is you've done products and what's it called? Products and reactants in chemistry. So you could also mix the fluorine or whatever it is with a product and a reactant. You can put them together and you might want to see how they interact, how they move. So if you have a Geiger counter, you can see, oh, my product has reacted with the reactant and has sank to the bottom of the solution, or something like that. Not really what is used here in physics. The example in physics is trying to find a leak in something here, but it also has a chemistry application of trying to see how the product or the reactant has moved through some kind of reaction. Yeah. Okay. This one is not as important for the exam, so you do not need to write this exactly as it is here, but I would like you to make some note of the concept here. Fluorine 18 is used. You put it in your own words, Mir. So like, for example, you could say a radioactive material is mixed with the water, so a Geiger counter can be used to find the leak. Something like this. You don't need every word here, just a sentence in your own words for this one. Why do you think fluorine 18 with a half-life of 2 hours is used? Why do you think this 2-hour half-life is used?
So that it does not react too much?
Yeah, so it doesn't stay in the water for too long. After 4 hours, a quarter is left. After 8 hours, so after 24 hours, it's basically gone. However, you don't want the half-life to be too short because it might take you an hour of walking up and down to find the leak. So 2 hours is a good amount of time for something like this. Yeah. You know what leak is? Do you know leak? Yeah. What did you write, so?
Fluorine can be used with water. From the Geiger counter can be used to find where it's radioactive, to detect where it's a pipe underground has a leak.
Okay. 10 out of 10 for physics, not 10 out of 10 for grammar. But that's all I care about. Yeah, good. Okay, you have this. We go to the next application. So the next application is in medicine called technetium 99M. Again, half-life of 2 hours. Why do you think 2 hours? So it doesn't stay in the body too long, but long enough so you can actually use it. Now, this person has been injected with this radioactive material. And this is used when an X-ray would not work. X-rays are good, but they only show you what? What can you see with X-rays? The bones, yes. You can only see bones with X-rays. So suppose you have something wrong with your liver, or your heart, or your kidneys, or your lungs. You can't use an X-ray, because X-rays only show you bone. You understand?
Yeah.
But if you inject someone with this, then everything in their body becomes radioactive. So you could see if somebody maybe has a hole somewhere, or a leak somewhere, or an organ is damaged. Do you know what I mean? Yeah. Now, this person here, you see he has two red areas here and here. And there's a reason for that.
Two more down.
And two more down through as well. I think these are more like around about the kidneys maybe. But there's two very bright red areas here and here. Now, does anybody know why here and here are red in the picture?
Because of cigarettes?
Not because of sickness. This will be for everybody.
Cigarettes.
You had this word recently.
Thyroid.
Thyroid. Yeah. Yeah. This thyroid, its function is to clear toxins from your body. So it's trying to remove the radiation. It's collecting here, you know. Also here, these also try to remove toxins as well. And you can see down below as well, he has a couple here, which I don't know if, I don't think they're the kidneys, they seem too low. Maybe there's some problem there he has. But there's another area as well, you see here on him. This part of the body, do you know? On the picture here? This part? Liver. Liver's job is also to clean the blood. I think, no, kidneys are for blood. Liver is to clean toxins as well. Yeah, but in your stomach, I think so, yeah. I just know for removing alcohol, the liver is used. So I think it's to remove toxins from the food, maybe. I don't know. Yeah, from your stomach, perhaps. Okay, so this is actually very common. Actually, your sister will know all about this. It's most common in diagnosis. It's what we call imaging procedure. So you can say technetium is used as an imaging procedure in hospitals. 4 out of 5 imaging procedures in hospitals are like this. You know, we always think of X-ray as being like the common one because everybody knows X-rays, but in fact, X-rays are really only used for if you have a broken bone. And when you think about the number of people in hospital, how many of them will be there because they have a broken bone? Not many when you really think about it. So this is the most common imaging process to use in a hospital. Also, this guy looks like he could lose a little bit of weight as well. I think that would help him out too. Huh? You can kind of see he's a bit big in the face. Yeah, he's got a bit of that going on. Now, you remember I said radiation is dangerous and getting it in you is quite bad. So why do you think it's okay to put this one in you?
Because it's used, yeah, half-life.
Still, it's in you for 2 hours.
Maybe the one that doesn't.
Yeah, maybe it has beta radiation, but still, you're putting radioactive material inside you. Not recommended. So why is it okay here? Any ideas?
Is that they have to say?
Yes, correct. At the end of the day, it's all about risk and balance. So if the doctor thinks there's something wrong with his liver, then it's worth taking the risk of making him sick from radiation versus him getting sick from an unknown liver problem. You know, so it's in life it's all about balances. Here you're exposing them to radiation which is dangerous and harmful, but the doctor believes it is more harmful not to know what the problem is, you know. So radiation is still dangerous to get in you, but it's all about balance.
Is there any way to take out the radiation from your body?
It will pass out of him naturally
Oh.
when he goes to the toilet, and the half-life is 2 hours, so in 24 hours you probably won't see the image anymore. Okay, continue with the next one. Yeah. Right, cobalt-60, half-life of 50 years. This one is used kind of like an X-ray, except, I suppose, unlike an X-ray, it can give you a bit more of a detailed image. Cobalt-60 releases gamma radiation. Gamma radiation, most commonly iridium, or in this case cobalt-60, is used to inspect materials. The vast majority of radiography concerns the testing and grading of wells on pressurized pipe, pressure vessels, high-capacity storage containers, pipelines, and some structural wells. Other testing materials include concrete. So what's happening here is the gamma radiation, if you want to think about it like this, you have your cobalt-60, and the radiation that cobalt-60 releases is gamma radiation. And then you have something like maybe a wall, and then maybe there's like another wall here, and then there's another wall here. And the gamma passes through. And you have some screen to detect where the gamma is. Oh, Sharif. Let me start again. You have your cobalt-60. The cobalt-60 releases gamma. The gamma passes through the material and hits a screen. Like a photograph, you can get an image here of what it passed through, like an X-ray. The difference between gamma and X-ray is gamma can give you a more detailed picture, because gamma is at a higher frequency than X-ray. So because it's a higher frequency, the result is it can give you a more detailed picture than X-ray. So it's better for a detailed picture. Disadvantage. Very harmful. Unlike X-ray, which is just harmful, this is very harmful. So this is why it's only used not on people, but on inspecting cargo. So here at the border, they maybe see someone is trying to take a gun into this country or whatever. You would see this used in post office in America, where they check the mail for any dangerous materials. The other advantage of gamma is if there was some poison in the mail, like anthrax. Do you know anthrax? Anthrax is a poison that some people have put in the mail and sent it to people they want to make very sick. If there was anthrax in the mail, the gamma has the benefit of also killing anything that's alive inside of it, because you're not supposed to post anything that's alive. So if you put anthrax in an envelope or a box, the gamma will kill it, because it's, very harmful to life. So cobalt-60 used for a detailed image. It's used in engineering to check pipes, to see if there's any holes in the pipes, any holes in the walls, any holes in the containers. Because you can see from the picture here, it's quite detailed. You could see clearly structure. It's quite detailed. And so if you can write one sentence here to summarize this, basically it's like a detailed X-ray, except more harmful, so not to use on humans.
It's a detailed X-ray.
Yeah. Like a detailed X-ray.
Is it used on humans at all?
I have a feeling it is, but maybe not cobalt-60, because I really think this is what they do at the airport when they want a detailed X-ray. Yeah. Now, not every airport. I've never been in an airport where I had to walk through some human-sized X-ray machine. But definitely this will be used when they scan your luggage at the airport.
Yeah.
Yeah.
They know everything.
Yeah. Disadvantage, if you had any photographs, nobody has it anymore, but the photograph film,
Yeah.
pre-digital camera, this will destroy it, the gamma. It will destroy the photographic plates.
You never been the scan?
Not the human-sized one. No, the metal detector, of course, but not the one that scans and X-rays you at the airport.
Oh.
Special security.
Except that you never been the
No.
Maybe you are a diplomat.
Yeah. No, I didn't get waved through the VIP section of the airport.
No, in the mall when you will go to between this.
That's into that.
Yeah.
They scan you at the mall.
Even in Pakistan also. The big malls, yeah.
Metal detector or X-ray?
Metal.
In school.
Yeah. Yeah. That's crazy. All right, you got this one?
Yes.
Yeah. Okay. So next application. Fighting cancer, boron 10 and neutrons. There's a couple of ways to do this, fighting cancer. The old way, I'll give you an example. You have your person here. This is my person.
Wow.
Yeah, I know. You get the idea. The person. Now, what would happen is the person maybe would have some cancer here, for example. So what they would do is they'd have many radioactive sources that would release gamma radiation. So gamma would come in here. Now, because the gamma is very weak, it doesn't really damage the body on its way to the cancer. And because this is very weak, again, it doesn't really damage on its way in. But they all meet exactly at this point. So at this point, yes, it's like you try to blow it up by firing at it from different directions. Disadvantage, has to be some damage on the way, but not much. Also, disadvantage is you have to be very sort of precise as you fire at this. But like I said, that's the old way to do it. There's this new treatment I was reading called boron 10, which I think is absolutely a really interesting way of doing it. You would have the cancer, and inside the cancer you would inject something like boron 10. Now boron 10 is not radioactive, so it doesn't hurt you. So you put boron 10 inside the cancer, and then you fire neutrons. Neutrons are quite harmless. You fire the neutrons, and they hit the boron 10, and the boron 10, whatever number it is, plus the neutron forms boron 11 plus, I think, a beta particle. Or I can't remember, or maybe it's an alpha, I don't remember. Anyway, the neutron sticks to the boron 10 and forms a boron 11. The boron 11 is radioactive. So what you do is you put something not radioactive inside the cancer, you fire a neutron at it, and you make it radioactive, but it's only radioactive inside the cancer. So inside the cancer cell, it becomes damaged from the radiation. But what is also great about boron 11 is the half-life is practically 0 seconds. It's tiny half-life. So you have the boron 10, neutron comes in, hits the boron 10, becomes boron 11, becomes radioactive, damages the cancer, and then almost straight away, the half-life is 0, means it very quickly becomes stable and not radioactive again. Do you understand?
But how can you?
Can I go for one?
Yes, yeah. How can you
How
ask?
can you fire the boron and fire the neutron?
No, you inject the boron 10. So you take a needle and you put boron 10 inside the person with a needle. Do you understand?
And then you fire.
The neutron. Yeah.
But you have to do it very quickly because the half-life is very.
No, boron 10 is not radioactive. It has no half-life. It's stable. It will just sit there. You fire the neutron, it becomes boron 11, which quickly decays. But as it decays, it releases radiation, which damages the cancer cell. You understand? Yes.
How long has this been?
Oh, I don't know. I think this is quite new. I was only reading about it a couple of years ago. I don't even know if it's available everywhere or if it's still in research. I just was reading about it and I thought it was quite interesting because most treatments of cancer so far is they fire gamma radiation in all different directions and it all meets at one point and like burns it almost. Whereas I just feel like this one's kind of maybe the way of the future because it's more cleaner, safer, accurate. I just think maybe one day this will become the normal way of doing it, you know. So radiation therapy is the general name for this, and it uses special equipment to send high dose of radiation or neutrons, in the new case, to cancer cells to destroy them via radiation. Most cells in the body grow and divide to form new cells. I don't know why I have that there, but cancer cells are the same. They grow, so you'd want to kill them. Anyway, a big difference between this therapy and chemotherapy. Chemotherapy exposes the whole body to drugs to try and kill the cancer. The side effect being that all of your cells are being exposed to the drug that tries to fight the cancer. What's nice about radiation therapy is it's only focused on the cancer site. Chemotherapy is just a blast for the whole body. So this is, chemotherapy is what they would use in a sort of last resort situation, you know, because it has some serious side effects. But again, like I said earlier, it's the doctor and you balancing your risk, you know. So I think the good thing is, from reading about treatments of cancer, is we're getting very, very good at fighting cancer, and I think now more people survive than die from it. Yeah. So like I think maybe 2 or 3 years ago, the percentage increased to 50%, meaning, you know, more than half of people who have cancer will survive. And that just increases each year, and it increases through different treatments like this. So it's really, I don't know, it's good application of radiation. Good application of it. So in 1 or 2 sentences here, you do know the word irony, don't you? Ironic. So there is a certain irony here that radiation, which can give you cancer, can also be used to treat it. It's quite ironic. Nobody here is doing biomedicine. That'd be more science, I suppose. Biophysics will be exactly this type of area, mixing biology and physics together. Okay, continue? No. Ms. Sharif, you'll have a lot to talk to with your sister about tonight when you go home, and what you learned today.
Yeah.
Okay. The next one now. Food irradiation. Cobalt 60 again. You recall I said cobalt 60 is used to scan equipment at the airport or at the borders. And I said one benefit of cobalt 60 is that if there was anything alive, like anthrax or a disease, it kills it. And in fact, that's why it's used here for something called food irradiation. I don't know if anybody knows this concept, food irradiation. You might be surprised to learn that this happens to your food. So, this is the problem. The farmer, let's say, collects apples, gathers apples, whatever, and they put the apples into storage, but before it gets to market, it's starting to rot. Or in the market starts to rot. Now, what's the reason for it to rot? Why would an apple rot? What's causing it to rot? Yeah, but what? Yeah, what is the mechanism?
Gas.
Could be gas, but you're thinking to chemistry, like oxidization or something. Keep it a bit more biological. Bacteria. So bacteria is eating the apple, and where would the bacteria be? It'd be on the outside of the apple.
Yeah.
So you would have your apple, and you can't see it, of course, but there's bacteria that lives on the surface, and this bacteria happily eats away at the outside of the apple, working its way in, and the apple starts to rot from the outside. So, the outside gets soft, and then it gets brown, and then it starts to decay. So, what they do is, when they pick the apple, they would fire some gamma radiation at it. The gamma radiation has two benefits. One, it kills the bacteria. No, three benefits. One, it kills the bacteria. Two, the food isn't really radioactive afterwards, because gamma radiation is a wave. So there's nothing to stick on the food. It just passes through the food. Unlike alpha and beta, which could, especially alpha, which could stick on it. So that's one advantage. It doesn't leave the food radioactive. One advantage. Second advantage, it kills the bacteria on the surface. But there's a third great advantage. Any insects that live on the apple, they will no longer be able to have insect children, because the radiation has made them they're no longer fertile. So the radiation kills the bacteria, cleans the surface, and if there was an insect on it, the insect may or may not die, but if it doesn't die, it cannot grow or have any more insect offspring. So, you might not think about this, but the food that you're eating probably had a dose of gamma radiation to keep it fresh. Cobalt 60. And you can see the foods that it's used. You can see vegetables, basically anything that's going to decay because of insects or bacteria living on it. So it's the process of exposing foods to ionization radiation. This treatment is used to preserve food, helps it live longer. Reduce the risk of illness, because that's the other thing. Your apple, if there's bacteria living on it, you're eating that, and that could make you sick. It prevents the spread of pests, which are insects, and delay sprouting or ripening, so it stops it changing. And irradiated food does not become radioactive, so it's not like you're eating something radioactive. Yeah. Now, again, it's all about balance,
So it's prevent illness or causes cancer.
Well, no, because the food is not radioactive afterwards. Because it's a bit like.
But you said there is a dose of gamma
Yes, there's a dose of gamma, but gamma is a wave that will pass through it. Yeah, it's different. Alpha is could stick on it, and that's very bad because then you're eating it. Because alpha is just 2 protons. No, gamma's kind of like an X-ray. Now, Musharif, even if it did make the food a little radioactive, which it could, it's all about balance, So if you don't do this to the food, you have a small risk of becoming very, very sick if something dangerous was living on the food. So sick that maybe you could die. So, life is not simple. It's all about balance risk, The benefits are more than the disadvantage because it makes the food cheaper. Does anybody know why? I was just saying, Mushrif, life is all about balance and risk. So even if there was some risk, the benefit is that you're unlikely to become very, very sick if there was something very bad living on the apple. Because, food poisoning can be so serious that it could be fatal or make you very sick for weeks, But it makes the food cheaper, which means more people can have more food. Why am I saying it would make the food cheaper? Why would the food be cheaper? What do you think?
Because you don't need to buy a fish, fruit.
You don't need to buy food as often if it lasts longer. The farmer doesn't need to grow more food if the food he has doesn't waste away, So again, maybe it makes food cheaper, which means more people can eat. So, like I said, life's not simple. It's all about balancing. So food irradiation, again, another use of cobalt-60. If you can write a sentence down here. So what you're doing is, does anyone know the verb for cleaning something to free it from germs? Sterilizing. Do you know this verb? No, okay. Cleaning the food to free it from germs using gamma radiation is what you could write down. It's like it cleans the food.
The last benefit, what is the last benefit?
Alright, so there's 3 benefits.
Kill and clean and then?
The insects. The insects cannot have children anymore.
Okay, what are the disadvantages of it?
Well, I suppose
Besides the risk of it may be radioactive.
Yeah, I don't even think that's really so much of a risk. Of course, whenever you're dealing with radiation, it's always a risk because perhaps the machine breaks and some cobalt-60 gets on the food. I could imagine that happening. I suppose if you do it too much, you might actually start to damage the food, which would be bad. Because you're killing the germs on the surface, but if you keep using it, then eventually you'll start killing the surface, the outside of it. Disadvantage, I suppose, yes, like I said, if the machine's faulty, maybe some cobalt-60 could get on the food. I don't really see many disadvantages. The biggest thing I would be worried about is making sure the person that's using the machine is qualified and knows what they're doing.
Is this application new? Well, because I know that people used to use chemicals before even taking the food, like adding it to the plant.
Yeah, I'd say this is not super new. But I have a feeling that it's probably not used as much as chemical treatment because it's more expensive than treating it with chemicals. But this is the funny thing. I'd much rather eat food that was treated with cobalt-60 than with chemicals because the chemical spray sits on the food and you're eating it.
Yes.
Whereas this does not leave a trace on the food. So if I had a choice between food treated with cobalt-60 or food sprayed with some chemical, I'd rather have the cobalt-60. So I see more advantages than disadvantages here. Okay, did you write something down for this one? Musharif? You got some? You wrote something down? Yeah. Okay. Right. Okay. Continue then. And the last one here is something very important, which is in bold now, called carbon-14. Now you all know that carbon has how many protons? It does not, absolutely, no, it doesn't. OMG.
It can have more than 14.
Which one? 60. Oxygen.
12.
Is it 12 protons?
6.
Oh.
6 protons, 6 neutrons, 12 nucleons, that's the word, I forgot. So carbon-14 has how many extra neutrons? 2 extra neutrons. So it's radioactive.
Yes.
What are you doing on your phone? Are you listening to me?
Yeah.
Are you?
Not much. I am with you until you say 6 protons.
Okay, let me continue from there. Carbon has 6 protons and 6 neutrons. This carbon-14 has how many extra neutrons? 2. So it is radioactive. It will decay. Where does the carbon-14 come from? What happens is there's carbon-12 in the air, and this carbon-12 reacts with neutrons coming from space. And through a process that happens in the atmosphere, the carbon-12 becomes carbon-14. So some of the carbon-14 gets into the plants. So the plants are now radioactive with carbon-14. And then, of course, what happens with the plants? The animals eat the plants. And now the animals have some carbon-14 in it. So basically, everything that has carbon-14 in it. But newsflash, everything that's alive is made from carbon. So everything that has carbon in it will have carbon-14 isotope in it as well. And then what happens is when these things die, it stops taking in carbon-14, and so the carbon-14 is now free to decay. By measuring how much carbon-14 remains in the dead specimen, you can age it. And carbon-14 has an extremely long half-life, meaning you can age things very, very far back in time. So radiocarbon dating is a radiometric dating method that uses carbon-14 to determine the age of blah blah blah. I have no idea how to say this. Carbonaceous materials up to about 60,000 years old. One of the frequent uses of the technique is to date organic. What's organic? Yeah, anything that's alive, yeah. Remains from archaeological sites. What are archaeological sites? The sites where people dig for history. This is important for the exam. Please write this one down as it is.
As it is?
Yes, because it's in bold, see? Bold.
Not in my word.
Well, no, you can a little bit, but I'd like you to make a copy of this in your notes as it is on the screen. Do you do any of this stuff in chemistry? Radiation doesn't really come up in chemistry. No, not yet, anyways.
Is there any chemistry in mechanical engineering? I hope not.
Mechanical engineering, unlikely.
Maybe a bit for the cost or something like that.
Yeah, I'd say maybe it has to do a semester of basic chemistry, like a semester. Because like Adnan was saying, you know, stuff to deal with oxidization and rust and things like that.
The first is the general engineering.
General, yeah, so there might be a semester of chemistry, something like this.
And a lab.
Huh?
And a lab.
A lab or two, maybe, yeah. You got this? Yeah.
That's it. I hope so.
Yes, just to say about the carbon-14 datum. I think it's interesting because you can use the carbon-14 to date things quite accurately, you know, within plus or minus 200 years. And when you think about it, a lot of things that you discover, like at an archaeological site, would have been alive at one point. So it has carbon-14 in it. For example, if you find a very old book, books are made from trees, and trees, of course, were alive. So you can know how old the book was. You know, if you found some example would be you found an old fire, and in the ground were some old fish bones. Well, of course, the fish were alive, so you can know how long the fish has been dead for. So you can know how old the campfire site was.
The rose.
Huh?
The rose.
The what?
The rose.
The rose.
Flower.
Yeah.
You can check all about it.
Yeah, indeed, yeah. Anyways, just before you go, it's funny because I got this picture, and only afterwards from looking at Google, I noticed this picture came from this website. And it's one of these websites where people believe the Earth is only 5,000 years old. And they were just trying to explain why carbon-14 could be wrong, because it kind of conflicts with their idea that the Earth is this old if you have something from carbon-14 that says it's, you know, this old here. But just before I go, on a personal note, I just think being physics students and science students, your responsibility is to what the data is and not pre-existing notions that other people have. So if you have a good theory of how something works and your data says this is the result, well, it's not your job to change the data or your interpretation to fit with some existing belief, you know. Because you know, for all the things in physics, you know, like remember Copernicus saying that the sun is the center of the solar system. He got into a lot of trouble for this because everybody thought the Earth was the center, you know. Yes, yeah. Well, no, I don't think he got killed for it. I think he got house arrest. He couldn't leave his home.
Who got killed for saying?
Oh, I don't. I'm sure many people got killed.
The Earth circle.
Yeah, that was the other thing too, saying the Earth was round and not flat. And I don't know if you've noticed this, but I believe that. There's a growing trend online
Right now, yes.
right now
The Earth is flat.
that the Earth is flat,
Yeah.
okay? As physics students, I expect you to be above all of this, okay? It's your responsibility to enlighten people, okay? So yes, the Earth is not flat. Okay, that's all. So, of course, the nice thing here is there's no homework for this, but the two most important ones for the exam are which two? Yes, which are the smoke detector and the carbon datum. All right, tomorrow, so.